Hey there, this is Rosnell. This is a tutorial on how to get started with Altium. I'll give a little bit of context and it's just so, I mean, if you don't know what I look like, you can come to me and ask for questions, but we can get right into it. Alright, so apart from the recording software, which apologies for that, this is the homepage of Altium, but you're probably not starting right here, so let me take you through how to install the software and how to kind of get to this page right here. So, there's a couple of things. There's the Altium Student Lab. This is on altium.com education/students. You can enroll here for free. And then you can put in your Columbia email, make sure it needs the .edu ending, and you'll get access to install Altium Designer and a license for the software for, I think it's about a year. But anyways, for additional context, I guess, like what is a PCB and why would you need to use it for senior design? A PCB stands for printed circuit board. It's closer to the final stage of your design where you're already have prototyped it, already have breadboarded your designs, you've already validated it, you're choosing more or less the final components, and then you're putting it into a more finished product. It's really useful in when you're considering packaging a circuit in a tightly constrained area, and then also it's really good at reducing noise. It's a pretty good point of mitigation because when you're using a breadboard, there's a lot of parasitic capacitances that are just induced by the nature of like the geometry of the packaging, and in a printed circuit board you have very precise control over the different layers, the dielectrics, and all sorts of different things that just make it better overall. So you definitely want to consider this to create a nice polished final product for whatever circuits your team is designing. For context, I have some example circuits. I've mainly worked on FSAE, so I have a bunch of FSAE projects in my Altium project space. And also, if you're part of one of the engineering clubs, there's also team-based licenses that you can get from them as well if you're involved in any capacity. But for example, I'll show you like one board. But this is kind of a 2D view of the physical stack up, and then this is a 3D view of the stack up. Basically, all these are different components on a circuit that you would have breadboarded, and then I'll take you through in this video a very simple circuit, not one as complex as this, but the schematic capture, the layout, a little bit of a component sizing, and then how to get your PCB ready to go for manufacturing, depending on what fab house you use. Alright, so that's enough with that example. Let's get started with our design. I want to do something pretty simple, but something that I think everybody might have to use for your projects. What I would like to focus the design on for this example to get us started is on a power converter, specifically a low dropout regulator, an LDO. Really what this is useful for, I won't go into too much detail, but if you're taking in like a battery voltage, you're using some type of battery in your design, and you want to ensure that your circuit gets a regulated output, so you don't want, as you're using the battery, the voltage to droop or change depending on what load you're driving. You use a voltage regulator, something like this, that will take in a voltage range. I think this is 2.5 to 6 volts, and it'll output a consistent 3.3 volts up to a maximum current of 150 milliamps, as it says right here. And when you're choosing your parts, there's a lot of things to consider, checking if it's in stock, if it's active, if it's available. But I just chose this part as an example. This doesn't mean that you have to use it, but we'll be focusing making a board that will effectively take in, through a connector, a battery input voltage, and then as an output, it will give you a 3.3 volt fixed voltage. And when choosing your parts, definitely go into the datasheet. I already have the datasheet open right here. And it'll give us a recommended application circuit, which will be really the focus of our design. And also one last thing that I wanted to mention that is going to be important is to choose your fabrication house. On Courseworks, there is a recommendation to use, I think it's like advanced PCBs, because it's a domestic supplier. You can, as far as I know, use different fab houses. Ones from China are typically cheaper, but say they sometimes have longer lead times. I've been most comfortable using the JLC PCB, like PCB fab house capabilities. And I want to highlight another thing that you have to take in consideration when designing your PCB is where you're going to be manufacturing it, because this is also going to give us a set of rules that we're going to work with. And this is just to put it on your radar. We'll come visit this at the end of the video, but you can go, for example, to JLC PCB, and this is a site that I'm going to, I'll link this in a Canvas post, but they have really useful stack of files and rules files. These are going to define the governing rules of the physical definition of our PCB. And so I have, for example, I have this rules deck file already downloaded, and this stack-up file, what that does is it's defining the physical dimensions of your PCB in terms of your layers. So there's, top and bottom layers, there's dielectrics in between, there's copper in between. So what are those exact thicknesses and what are the exact dielectrics and values that are required for it? This is typically useful for modeling, but when you're making your fabrication outputs, it's also important information to have. All right, but without further ado, assuming that you have your license in, you're able to log in and create your Altium account, let's get started and create a new project. All right, so we're going to go to File, Project, New Project, and you'll see that there's a bunch of different options right here. I'm connected to the Formula Racing Cloud, so I have the option to create a project in this cloud space, but I'm not going to do that. For the purposes of senior design, I would recommend creating a local project. The neat thing about Altium is that it has a Git version control system already like embedded into the software. So when you create a local project, you can actually share your project with your other teammates, and then you can actually work on the schematics and the layout all at the same time. So it's super collaborative. You might not have some of the options right here. These are such custom things that I might have, so don't worry if some things don't look exactly the same. But for now, we're just going to call this test project. And then note wherever this is on your local file directory, you can go to this directory and then zip your project files and also send it between each other if you so please. So anyways, we're going to create the project now, and you'll see on the left, you can kind of ignore the other projects that I have. We're just going to focus on this test project right here. But when you create the project, that's not the only thing we have to do. Now we have to go to File, New, and we are going to start off with a schematic. In general, when you're designing a PCB, you always want to start with your schematic capture first, and then move on to the PCB, board shape definition, and ultimately the layout. To get to this point, you should have already simulated your circuit, chosen your components, and this is really just the final, basically painting the final version of your circuit into the software and creating the associated component links that we have to do. But this should not be your first draft, is effectively what I'm trying to convey in terms of the design cycle. So there's a lot of things you can customize in this view. This is kind of a callback to old school schematic drawings. This is like a standard schematic drawing size. You don't need to use this template. You can always edit it. The way that you can kind of navigate through different panels is by going to the bottom right to this panels page. You can click on it, and then you can go to properties. And this gives you the properties of the entire sheet. You can choose formatting and size right here. There's different templates that you can choose. So on the CUFR cloud, we have some standard templates over here, and there's other ones that are already preloaded for you. You can choose different standard sizes. I won't focus too much on that. I'll just keep it at custom and then do a standard 300 by 200. In general, it's kind of recommended to keep your schematics nice and concise, and then if you need more pages, there's different ways to do that, which you can come and talk to me in office hours, but I won't go into depth just to not overcomplicate things. Anywho, we have our new drafted page here. Let's start populating this with some components. So, a cool thing about Altium Designer is that you don't have to go searching for custom parts and footprints like you do in KiCad. You can actually use the manufacturer part search. So, you can go to Panels again, and then select the manufacturer part search. Actually, I already have the part looked up right here. And ideally what you're looking for, whenever you're looking for parts, you can go through different categories, whether it's capacitors, ICs, passive components, stuff like that. You just type in the part number, so not the one from the supplier, but the specific one from the manufacturer. And you want to make sure that it has a kind of like a green line right here, and it has like the chip symbol like not crossed out. This means that you can actually use the symbol and footprint in your circuit or in your project. You can even verify this, so it shows that there's a symbol right here in the Models tab when you look in the Properties pane, and it also shows you that it has a 3D model with like copper pads and stuff. So be sure to check that. It also gives you nice information too about like how many are in stock and how much they cost, which when you're working at scale is really important, but don't need to worry about that right now. So you can double click on this, or I think just drag, yeah. So you just drag this guy, and now we have our linear dropout regulator. Now what we have to do is define a couple of inputs and outputs. So how are we going to do that? Well, especially when it comes to stuff for power, it's recommended to check this top menu. This drop-down menu will give you an array of options when you right-click on different power ports, and these are global ports, so these are accessible throughout your entire sheet. We're only doing one page right here, but if you use multiple pages, which I can show you how to do like one-on-one or just more in depth, these are symbols that are effectively global. Think of them as global variables. I want to show a distinction actually between that and let's see right here, I'm trying to find the right option. So on this one with the wire bus, you can create a net label, and a net label is similar to one of these power ports, but a net label is a private, kind of a localized node. So it only exists in this sheet. For the sake of good convention, we're going to use one of these power ports. Here, we're going to create a VCC port on VIN. But we're going to rename it because we know that this is a battery input, so we're going to say plus bat. Then you can use the Control W command, and then you can go to where the pin is. You'll note that there's a connection because of the red X, and then you'll make a connection between the power port and the input. Perfect, just like that. Then we're going to want to connect ground of our circuit. So you can do that by right-clicking the power port, creating a ground power port, and this is a standard like IEEE symbol or something like that. So now that's labeled, and now finally we want to create our V out. Our V out is a fixed 3.3, so we can take a generic power rail like a VCC and just rename it. By the way, I'm just double clicking on these components, like I can also double click on this symbol, and it'll open the properties panel right here. If for any reason you're not seeing it, remember that you can go to the panels, click on it, and then you can select which panel you want to show up, right? So that whether it be the part searching or the properties of a particular component, and again, when you don't select anything, it just shows you the properties of the whole page. Anyways, going back to this power rail, let's make sure to rename it. I'm going to call it plus 3v3. If you're not familiar with that convention, this is pretty standard when you're looking at schematics and defining rail voltages, because a decimal point on a schematic from far away just looks kind of confusing. It's best to just indicate voltages like 3.3 or 5.5 as 3v3 or 5v5. Alright, so now pressing Control W again, I'm going to connect V out, and now I've defined that power port. Now, let's take a look again at the schematic. So going back to the recommended application schematic, we see that we've labeled our ground, we have our V in labeled, we have our V out labeled. There's also an enable pin, which we can make it as a net label. So let's do that as well. Alright, I'm going to extend this out with a little wire, and then I'm going to right click on this drop down menu and then create a net label. The default name you probably shouldn't use, make it something a little bit more intuitive, and then you can rename this as EN. Cool. This is good for organizational purposes. Now one tip that, actually before I do that, I want to show you another thing. So this NC pin is non-connected, it's not used at all in the chip. You can discriminate, or basically like make it so that the Altium itself doesn't give you any errors if you don't have a connection on this node by going up here to this part right here and do a generic no ERC. A generic no ERC is basically one step of the schematic validation process that I'm going to show you where it validates your schematic to make sure that you don't have any errors in your symbol definition or in the creation of your footprints and stuff like that, which might all sound pretty new, but it's just a way of basically saying ignore this issue. So we're going to put it on pin 4 like that, and now that is connected. Alright. Now, one thing I also want to show is we want to make sure that these ports are connected. Sometimes if there's junctions, like for example, if we zoom into this ground port, I'm pretty sure that this is connected, but if I really want to be sure, I can go to the left panel and click on the navigator and click on interactive navigation. And then from here, I can click on a node in my circuit and it'll highlight everything that's connected to it. So here ground is definitely connected to pin 2 of the IC, and I see that it's not connected to anything else, so it definitely won't give me an issue. I can do the same thing for 3v3, making sure it's only this one, EN, make sure it's only this one, no connect is not connected to anything, and then battery is just connected to this. Sweet. Alright. So to move out of this, you can just press escape and then click onto any part of the schematic. One other thing that's pretty useful if you have a much larger schematic, which most of you probably will, is you can click on these 3 dots right here and then click on the connective graph option, press apply, and then when you click on interactive navigation again and then choose a node, it actually shows you a graph of all the nodes that are connected to different components. And you can imagine if I had battery distributed to all a bunch of different ICs and or a bunch of different inputs, how large that graph would look like. All right, but let's clear out of that view. The way to remove that is to disconnect this, press apply, OK, go to interactive navigation again, click on that node, and then press escape. All right, so we have our linear dropout regulator, but one component does not a circuit make. So we actually need a way to interface this with the real world. So we have to choose some connectors, right? We can't just put this on a board and then not give it any way to interact with the world. So let's go back to the manufacturer part search. And I'm going to haphazardly choose a connector. This is not the right design methodology. Typically when you're choosing a connector, you want to consider the wire gauge, the ampacity of the signals, and the power that you're pushing. Also human design, you want to consider pitch between your connectors and also distance between your components and the connectors to make sure you can actually use this thing. But this is just for demo purposes, so I'm not really going to think about that right now, but heed my warnings. Anyways, you can go to this section right here where this says connectors, and if I didn't put any type of filter, so it's just going to give me a bunch of connectors. But I'm just going to choose one that I think looks good. Let's see, kind of scrolling. Maybe we could do something like, I don't know, like this one. This one's a little bit too much. This one has 3 connections. So this is a generic, like kind of, I guess, female header. We can specify this a little bit more. So actually we could use the 3 input header on our input side. So let's go back down to the PHF. This component, we can bring it in. Again, you just drag it. And we want a 2-position connector on the output side. So I'll do 2-pos connector. A little bit redundant, I suppose, but it should be fine. And I don't know, this one looks okay. This was just 2 headers. Maybe it's like it has a pitch of 1.27. I don't really mind. So let's bring that one in too. Awesome. So now we have our input and output connectors. So let's get on to defining them. To take a component and then I want to rotate it, you can press the spacebar and it'll rotate it like so. And this is a fine orientation for me. I'm going to extend the wires out. So I'm going to do it like so. By the way, I just want to make a quick note about the grid. Now, you probably don't like what I just did because it's definitely off the grid. You can set your own grid. Believe that should be on, let's see, on view. And then you go to grids, and you can cycle the different presets of grids, or you can set the actual grid yourself. So this is at like 5 millimeters. I can make this 1 if I wanted to, just for additional flexibility. But I would say in general, in a good design practice, yeah, definitely don't do this. Not because your circuit won't work, but it's just more of an aesthetic thing. But I will refrain from leaving any comments. Anyways, we have signal 1. I'm gonna bring this connector a little bit out here. I'll bring out signal 2. I'm actually gonna do a little fan out like that as well. Yep. And then I'll bring out signal 3. So I'll say position 3. You can, oh, by the way, you can take these ports, you can control C, control V, and then it'll just copy paste. I'll put pin 3 as the battery. Pin 2, if I extend it over here, oop, I want to remove that excess. Pin 2 is going to be enable, and then pin 1 is going to be ground. So I'm going to copy this. And again, if you want to verify connectivity, tap on this node, oops, I guess on the wire itself, and then it should show you that all these nodes are connected. Same thing for this wire, enable is enable, and ground is ground. Alright, now for our output side, again I'm going to choose a connector, I'm going to rotate like that. Let's say I don't want the order of the pins to be this way, I can press Y, and it'll do a vertical shift. Alright. So now, pin 1, I'm going to extend some wires out, right there, and then I'm going to copy paste 3v3 rail right there, and then I'm going to put ground on the second position of this connector. Nice. Cool. Alright, so schematic looks pretty good. If I double click on the components, you can see that there's footprints associated with all these parts. When you go to properties, you can show the different models there. It'll show you a nice 3D model, show that there's like pads that exist for this design, and overall this is looking pretty good. Some additional notes that I probably would recommend is cleaning up the schematic a little bit, but we gotta add a few more components, and then we'll be right on our way. Alright, so looking back on our schematic, it looks like the only thing that we're missing are a 1 microfarad 10 volt capacitor and another one on between the inputting ground and another one between the outputting ground. So let's choose those components and we'll be on our way. So again, going back to manufacturer part search, I can clear my filter and I can go to passive components and I can just type in 1 microfarad capacitor. And something important to note is the package size for passive components. I like this package size. It's a 1206 package that's rated for 50 volts. It seems to be well in stock. Has a plus minus 10% tolerance range, which shouldn't really matter for this application. If you look at this particular LDO, tolerances should be okay. Has a symbol and it has a footprint associated with it. It's pretty much everything that we want. I will say, if you're new to PCB design, I highly recommend sticking to a 1206 metric package size for your passive components. It is very difficult to design with smaller package sizes, and you should really only do so if you're willing to be okay with kind of the manufacturing problems that you have to undergo. This is not like a solving problems with the circuit type of issue. This is rather it is very difficult to solder and manufacture your boards if you go smaller than 1206. So only do so if you already have experience with it. Alright, otherwise I'm going to drag this component in. It's going to come with this nice cap symbol, and I'm going to drag another one in for the input. Alright, now I'm going to double click on this component, and I'm going to hide the comment for the particular part number, just to clean up the schematic a little bit. Same thing for here, I'm going to hide it. As you can see in this property, I can hide the comment of the part number. And now I'm just going to maybe fix up the position of the cap, make a junction right here, and then make a junction right here. And that one actually doesn't look that good, so I'm going to try to maybe fix this up a little bit right here. There you go. Slightly less intrusive line. Alright, So one right there, and then same thing for the battery. Going back here, and I'm just going to instantiate the ground symbol on this side since it's not symmetrical completely. Alright, nice. So, we have our components. These are all sized appropriately to be 1 microfarad. Actually, for additional clarity, instead of putting the part number on it, we can maybe add a comment about the value of these capacitors. So, we can make this 1 microfarad, just for clarity's sake. Alright, pretty good circuit. Now, all that's left are the high-level aesthetics. So, we have the main converter here. One thing that I like to do is I just like to make boxes. So, for example, I'll take the line tool and I'll just make a box around this component right here. Cool. Make a nice little component. Then I'll go here, I'll create a text string, and then I'll right click and I'll say this is the input connector. You can customize the font, the size, and everything of this guy. You can make it like really big. So we can do something like that. And I'm going to copy and paste and kind of do the same kind of labeling scheme for the rest of the components. So make a nice little box. This is generally standard practice when you're working with other people. You want to make sure that your schematics are readable. It's kind of like adding good comments in code. Labeling your schematics, putting down important information. I will say you can do stuff like leaving notepads, so like little sticky notes. It's kind of like you can leave a little note for yourself or for your teammates on what you need to work on. And then one other thing that's also pretty useful, but you can only do in a cloud setting, is you can add comments. So kind of the way that you would add comments about people's code, or when you're collaborating in Google Docs, you can do the same thing on your schematic. Alright, so let's get done with labeling. Oh, and by the way, all these additional features and stuff, there's so much that I can't really go over when I'm trying to make a shorter video, so please ask me questions and I'll be more than happy to help you. Alright, so we have our LDO block, and then we have our output connector. We have our output. Oop, switch to the Chinese keyboard by accident. Alright, for our output connector, I'm going to move the box itself right here a little bit closer in. And let's see. Alright. Yep. I always say that a good design is one where you pay attention to the small details, because if you care about the smallest details, then you care about everything, really. Cool. Alright. This is pretty good. You can put your name in the corner, add extra text boxes. You can also import images, I think. Yeah, you can import graphics and stuff, which is pretty funny. But cool. We have our schematic. So what now do we do? Alright. Let me show you the next step. So go ahead and save your project. You can save it up here, so save it right there. This is in the test project, call it sheet 1, sure. Name doesn't really matter. I'm going to close some other tabs so that I can show a little bit more freely, but I think this is fine. These are just schematics. Alright, cool. So what to do is the next step. We're going to go to, let's see, oops. We're going to go to project. Make sure you have the projects tab open. We're going to go to tools, and what we're going to do now is we're going to annotate our design. We're going to, basically what annotation means is you can see that these reference designators right here on your parts, they have question marks on them. When you're doing PCB design, let's say you're manufacturing this at a large scale or even at a small scale, this is indexing each one of your individual components so that they have basically a name on your bill of materials. And this is necessary in order to properly label them in your PCB layout, so this step is important. You basically want to go to annotation, go to annotate schematics. And this menu is really powerful. You can choose specific annotation schemes that maybe make sense for your particular project. I can go through the more complex options, but of course, reach out to me if you have any questions. What we're going to do is we're going to update the changes list. It's going to confirm that 5 changes were made, and then we're going to accept changes and create an electronic change order. In a company, this would have to be like validated by like the chief engineer or something like that. But in this case, you are the chief engineer. So go ahead and validate changes here. Pass all the checks. Then you go to execute changes, and you should pass with flying colors. Wonderful. Now I can close, and we can see that our circuit looks pretty clean. One thing that you'll note, and you might run into this when you're doing your schematic, is that you might have like red squiggly lines over certain components. That usually indicates that there's an error in either the way that you've defined your component or in the way that you're trying to use the specific node that you're working with. Usually when you highlight on a component, it'll tell you what that error is. Here it just tells me that it's a power object, that it's what the net name is and stuff. But if you run into any obscure issues, check some of the forums first, but I know, of course, happy to answer any questions as well. Alright, so now we can save. Our schematic is looking good. Now we can get on to the next step. One option you can do right here is also you can create an active BOM. This is really only useful if you're meticulously choosing out your components through the manufacturer part search. If you're using custom components, it might be lacking a lot of information, but I'm not going to create it right now. But this is related to, for example, when I pick this particular component and it tells me what stuff is in stock. The active BOM is very useful on telling you what suppliers have access to this particular part, or whether they're running low on stock and what the prices are. And so you can even order directly from Altium if you really, really want to. But depending on the project and the scope, sometimes this is not a reasonable approach. All right, now onto the PCB. We're going to go to File, go to New, and create a new PCB document. Awesome. All right, so we have this blank page, and it's kind of a little bit confusing, but there's a few things we have to set up before we get deep into the PCB. On the bottom are different layers, and basically the way I want you to think about this is imagine, and this is familiar for anybody who's done the IC design, is that you're laying different layers of copper on top of each other when you're working on your PCB. So you define the board shape, you define the dielectric and everything, and then you're putting copper on top of copper, and you create vias that route through these different levels and connect stuff together. But like any type of technology, we have to define what we're working with. So let me show you how to do that. So inside your PCB document, you can go to Tools, and first we're going to, we go to Design, and then we're going to define a few core parameters. Go to Rules, and what this contains is all of the rules that are necessary to ensure that your design is manufacturable. This does not check that your design is correct, that's up to you. This just makes sure that it's capable of being manufactured by the fab house that you have chosen. And again, I chose JLC, so I'm going to be using the rules files. Bring back up the old website. I'm going to check to get the rules deck from this particular fab house from JLC PCB, and I'm going to use this rules file. I'm also going to use the 4-layer stack up for this particular project. So going back here, when I'm into the rules window, I'm going to right click on this folder, I'm going to import rules, then I'm going to hit Control A and select all the rules. Hit OK. Now I'm going to go down and find my particular rules deck. I use JLC PCB for FSAE work, so it's going to be in that folder. I'm going to click the .rules file, and then it's going to ask if it's okay for me to clear the existing rules prior to the importing. Hit yes, and then go ahead and apply. Cool. Now all of our parameters are synced, and whenever you get a what's called a design rules check error or a DRC error, you're going to know that it's verified to be consistent with your fab house. I'm going to go ahead and save that parameter, and it's going to ask us to save the PCB document file. I'm going to go ahead and say yes. Now, one more thing we have to do is we have to define the physical stack up of our PCB. The way that we're going to do this is we're going to go to Design, go to Layer Stack Manager, and we're going to be greeted with This window, you can go ahead and close it, but this is showing us a layer by layer breakdown of our PCB. This is a pretty generic template, and you can actually choose to use the different templates. So if you actually click right here, if you go to rigid flex, which is your standard parameter, you can go here and you can choose to edit these different layers, or you can go ahead, add different dielectrics. You can even choose different presets and things like that, but we are not going to do that. Today, I'm going to use the presets, which I recommend you use as well. And we're going to load StackUp from a file. So we're going to use the provided JLC StackUp. I'm going to use it for a 4-layer board, even though realistically this board does not require 4. You can hit load from StackUp, and then I'm going to go to, I think it says FSAE. I'm going to click on 4-layer StackUp, and it's going to give me a bunch of different files. Basically, what these are distinguishing is your thickness of your board. So you can actually choose that when you're manufacturing it. The standard size is a 1.6 millimeter thickness. I recommend going with this preset, the 2313. It's the one that I've used most often for my projects. These are slightly other StackUp processes, but again, use whatever your project deems appropriate. So now we click that, it's going to change the different thicknesses for all of our different StackUps. For the dielectrics, it's going to give the proper values and stuff. And this is important if you have a workflow with like an electromagnetic simulation software, but we're not doing that one today, but it's good to have this configured. So we have our document, and now we have our StackUp configured. Now, actually, this is what's called the 2D view, this like black canvas of your PCB. If you hit 3 on your keyboard, you can actually see that this is a generic kind of green board. And because we've already defined our StackUp, if you hit Shift and then right-click on these arrows to kind of shift, you can see that we've added, there's a thickness. There's a thickness to our PCB that we've created by defining our layer stack. Right, so this is should be 1.6 millimeters in thickness. All right, to go back to the 2D canvas, which is where you'll mainly be working in, you just hit 2. All right, pretty good. We're at a pretty good starting point. I want to explain what some of the layers are. I'm not going to talk about all of them necessarily, but just to get you started. The layers that are copper or your conductors are usually the first 4 or the first 2 or 6 or however many you need. That's our top copper, our 2 internal copper layers, and then a bottom layer. So this is where we'll be making most of our electrical connections. And then mechanical layers are defining, for example, the board courtyard, and like different shapes and hole cutouts and things like that. Top and bottom overlay are where you can add silkscreens, which I'll show you in a second. And then these rest are related to the manufacturing processes, which you usually don't have to edit, except for in special circumstances. All right, so what are we going to do? First thing we're going to do is we're going to make sure that we have all the components that are related to our schematics. So the way we're going to do that is we're going to go to Design, and we're going to import changes from the test project. So this is the project file. You're going to see all the different things that we did on our schematic are going to show up here. You can double check these, there's not too many changes, but we're going to validate it. Most things are going to pass, and then we're going to execute. And then we all passed. Now, as we see right here, we just have like a few components, so we can make this PCB pretty small, honestly. I'm going to select all of them, and I'm going to move them. Alright, now immediately I can kind of see that there's an error in terms of clearances. Whenever you have a green, or it might be in a different option, a different color, I will say as a disclaimer that I am colorblind. So some of the different options and configurations might be in different colors for you. Apologies. Let me know if you see anything different. I can always help. I just have it in like an accessibility mode for myself as well. But I can see that there's basically a DRC violation with these green X's. I can right click on this for now. You really shouldn't do this, but for the sake of just kind of going through with the video, I can show you how to clear a violation. You can right click on it, click on violations, and then click on this particular issue that it's having. So it's telling me that there is a violation in terms of the clearances for this, and this is in units of thousandths of an inch or mils. I'm going to waive this violation, And if you're using a version control, this will keep track of whoever is clearing these violations. So this is a good thing to keep track of. I'm going to click OK and kind of move on from that one. But you probably shouldn't do this. Verify that your fab house can work with the constraints that you're setting, but I'm just showing you all the different options right now. Alright, we have all our components, but now we have to define what the size of our board is. The way to do that is to click on the mechanical layer, and then you're going to start either placing lines or different shapes. Here you can just directly create a rectangle, so I'm going to just do that. I will say that if you're working with mechanical constraints, it is possible to create curved edges. For example, if you go to, apart from arcs, if you are creating a line and then you hit spacebar, you can choose like the different orientations of your lines to go through. And then one way to do that is to create a line, stop it right there, and then you can do basically an arc from an edge. Oops, sorry. You can create, an arc from here, and then you can press spacebar to change the if it's going out or if it's going in, something like this. So you can create lots of weird geometries. In terms of my experience, I would say that creating custom shapes within Altium itself is a little bit clunky. I would recommend instead of using a drawing software to create a file, board cutout in a DXF, and then from there importing a DXF, which you can do by going to File, Import, and import a DXF/drawing. That'll import it. You can choose the mechanical layer as the layer to import this drawing into, and you can use that as your board shape, as I'm going to show you right now. But that's just a recommendation, I would say. Definitely try to do that. Alright, so now what are we going to do? We're going to basically create this as our board shape. So everything that is in this black canvas is the board. Everything that is gray is not. So we want to make sure that we have this defined. So I'm going to click on it. I'm going to go to Tools, and let me just make sure. Oh, sorry, it's in Design, so go to Design, go to Board Shape, and then you're going to click Define Board Shape from Selected Objects. Alright, now you'll see that only the black canvas is available on inside this mechanical layer. If I click 3, you'll see that now we have a much smaller rectangle that we're working with, and this is where our board is, but you can also see that we have our 3D models from our components imported too. Awesome. Alright, so now what we're going to do is we're just going to place our components wherever we see fit. Alright, so I'm going to put my connector a little bit close to the board edge. This is where the battery input is going to come in. I'm going to put my LDO in the middle. Same rules apply for like interfacing with stuff. So like you can press spacebar to kind of rotate something. I don't recommend mirroring footprints because especially if you're using stuff that has a particular polarity or indication, which is why, for example, it has this little dot on the chip. It might not work if you mirror it and put it in a different orientation, so please be careful with that, up to your own risk. For these decoupling capacitors that are added on the input and output, I recommend doing something like this, and then keeping stuff as close as possible to your chip. Transmission line effects and such. Do the same thing for the battery. I'm going to give it a little bit of clearance though, and I'll show you why. Alright, and here we go. We have then J1 as our output. Alright, cool. So, now we have our components laid out. I'm going to give you some tips now on how to do a proper and concise layout. First thing you can do is you can kind of move these silk screens. So if I go to the 3D view, you'll see that these are going to show up as little comments on top of your PCB. You want to make sure that these are all on your PCB, otherwise you can right click on them and just hide it so that they won't show up in production. But you can just move them around, make your PCB look nice and prim and proper. I'm not paying too much attention to that right now, but you should definitely for your designs. I'm going to move these a little bit closer, something like that. Cool. And now one thing I want to show you is for routing, it's going to be very often that you're using maybe a single rail, two rails, but definitely like a ground and some type of power distribution on your board. And if you want a really easy way to distribute that throughout your entire like design, one way that I like to do that is I like to choose a copper layer. So for example, I'm going to choose the bottom copper, and then I'm going to click on this option and place a polygon plane. I'm going to choose a polygon pour after right clicking, and what I'm going to define is a big area, and I'll show you what I mean by that in a second. So I'm going to start to create a big shape right here. Big shape. Right, and then I'm going to zoom in and make sure I close this line. It doesn't have to be clean. You should try to make sure that it doesn't have any weird shapes, but once I press escape, you're going to see that this blue blob has kind of covered everything. I can go click on the top copper layer and it'll show me the components again. But you should know that if you move your layers like on top of each other, like if I move the top overlay a little bit farther up, it's going to be more visible, for example. But going back to just show all the copper layers, what I want to do is I want to basically make this copper, what I've done is I've just laid out a huge slab of copper, and I want this to be the main ground connection. The reason being is that there's a ground connection required for all these capacitors and the inputs and outputs. So I just want a nice smooth return path. In order to define that properly, I'm going to choose the bottom layer again. I'm going to right click or double click on it on the polygon, and then I'm going to set the net to be one of the available nets I've defined in my project. So I'm going to set this to be ground. I'm going to repour the copper, and you'll note something interesting happens after I repour. If I go back to this visibility, is that you'll see that everything that is a through hole that goes completely through the board is now connected through the ground plane. This particular type of like cross hatching like this is a thermal relief. This thermally isolates this pad from your copper pour, so it'll help you when you're soldering your components because it's not going to add to the thermal mass and then just like kind of make it difficult to solder on. But it does have some inherent like voltage drops and resistances because it's not a clean connection to ground. But I'm going to leave it as default right now and kind of move forward. But this is kind of why there's like a hatch right here. Now, this makes it really easy to create ground connections because instead of having to connect a wire from here to here, which I'll show you how to do for the other connections, instead I can just basically drill down to the copper plane. The way that I do that is by choosing the plane I want to interface with, so the top copper layer, I'm going to click on this pad, hit Control W, and then go from the center pad and kind of bring my connection out, just like that. Then I want to create a via. Via is basically just a drilled hole that connects copper material from different layers together. So I'm going to go to this thing, this item, click on via, and then place this down right there. You see there was a momentary DRC error, so gotta be careful with those. But you see right there that because I created a via between the bottom layer, which is covering this expansive area, and then this trace, which also requires a connection to the ground node, it immediately created a connection between the top layer and the bottom layer, so 1 to 4, recognizing that it's the ground node. We'll want to do the same thing for the rest of the ground connections, so I'll do the same right here. I'm going to create, I'm going to copy this via and then place it right here, create a ground connection. Same thing right here. There's lots of good design rules of thumb when you're designing PCBs that I don't have a lot of time to get into right now, but I'd be more than happy to talk about them with you all. All right. One thing that I've noticed is I'm kind of blocking this pin, so I'm going to go ahead and select all these components in a group and then just kind of move them. So do something like this. This would be good. All right. And then I believe that's all of our ground connections. So now we can focus on making the other traces. In terms of the enable pin, this is a pretty low current connection, so kind of the default width of this trace, or of this wire, is probably enough to carry the current required. So you see I've made a connection right there. Now for the battery maybe is a little bit more current. I'm not too sure what the project specs are, but what I want to do is I want to go to panels, and I want to go to properties, and then now in the empty space I'm going to press Ctrl W, and I'm going to get a bunch of different options for how I want to create this this trace. Oops, sorry. So what I'm going to do first is I'm going to create this connection, go connect to the battery. You'll see that stuff that is not the same node is going to be highlighted in white, or maybe another color depending on what options you have. And if I double click on this, it's going to tell me what the width of this is. If you're not comfortable in mils, you can always change the units as well. Go to view, and then you just toggle units right there. I'm more comfortable with millimeters, but you get accustomed to using mils when you're working with PCBs for a while. Alright, so it's a 0.381 millimeter trace, and this is pretty small. It's definitely not the minimum that JLC can do, but especially because this is power, I want to just kind of increase the thickness a little bit. So I want to actually choose the entire track. So if I do shift and select all the copper areas, I can increase this to even like 1 millimeter. Maybe that's a little bit too much, because now we're starting to see that we're encroaching upon a lot of the areas of the capacitor and such. So maybe we can do 0.5. Alright, 0.5 seems to be doing the job. Alright, now we'll do the same thing and kind of make a trace that's similar track width. You'll see that because I've already configured it for this node, it's already set at the proper track width. And I just want to kind of straighten out this junction, kind of like that. Something important to note when you're manufacturing is, though manufacturing capabilities have advanced pretty far, if you do kind of exotic shapes and weird angles and stuff like what the junction looked like before, you run into the issue of having acids that are used to etch the copper out of this board getting trapped and creating defects when you're when this is like finally manufactured. So you want to kind of avoid that by just trying to choose simple geometries as much as possible. This is definitely not the 80s. Technology is much better, but you definitely don't want to give your fab house a hard time. Alright, so the final connection is now the 3v3 node. So this is already configured to 0.5 millimeter track width, and we can kind of stick with that one. Alright, awesome. We have all of our connections laid out. Seems like everything is dandy. You can definitely, as a final touch, leave some Easter eggs. Here I'm just going to say, Senior Design Test. And I can just change the text height. I'm going to make this like 1 millimeter. So something like that. Then I can hit 3, go to the 3D view, and I have my little circuit right here. So you see this is where I've made all the holes for my vias. And you can see how with the stack up that I've created, it shows you the definitions of your different holes and your different via connections. Pretty neat. Right. You can see the copper plane as well. Oops. You can see the copper plane as well, and like how we've defined the different copper layer definitions from before. So going back to the 2D view, we have a pretty set circuit. All right. So what's the next thing we got to do? We got to make sure that this thing is manufacturable. So after you save your design, you're going to want to go to Tools and do a Design Rules check. This is going to go through all the DRCs from the manufacturer and then just tell you if your design is ready to go. What you want to make sure you have at the top is make sure that you create a report file and then just run the design rule check. Here. Then this is going to create this document. It'll be saved onto your folder. And right now we only have one waived violation. This is the one that I kind of removed from before. But if you have any DRC errors, they'll all show up right here. And the cool thing about them is if you click on them, it actually zooms into the violation that you're having an issue with. So if anybody has done the digital VLSI class, this is a much better system than doing DRCs for integrated circuits, because it'll actually tell you where the issue is. Maybe that's just my experience, but
Our design is DRC clean, so I'm going to close that file. And now we have a ready to go design. So our next step is honestly pretty fun. All we have to do now is generate the proper output files. I will say that this is going to depend from manufacturer to manufacturer, um, but I'll just show you where you can get it and where to send your designs. Um, Depending on the fab house that you choose, maybe it's JLC or maybe it's somewhere else, these instructions are really going to depend. But once you're ready to go, in your PCB document, you're going to go to Fabrication Outputs, go to select your Gerber X2 files. A window will show up. You're going to want to make sure that all of these different knobs and dials are set to the proper specifications of your manufacturer. I believe for JLC it's in inches, and then it should be 0.01 mil, and then you want a .gbr file name extension. I'm not going to show the project outputs right now, just because there's so many different options. It might not be worth our time. But after you do Gerbers or some other type of output file, you'll also want to create a drill file, and then there's other types of files, outputs right here. Anyways, I just don't want to get into it too much for the sake of time. But just to show kind of the final part, once you have all the required files for your fab house that are ready to go for your PCB, you're going to want to then go to your fab house's main website. This is for JLC PCB, and in JLC PCB, I believe to be the easiest one to get an instant quote. You can go here and you can upload a Gerber file, and then you'll want to put in all of your specifications for your PCB. If you provide all the necessary files, which are kind of there explained in this guide, which I'll also link as well, how to export the PCB Gerber files into the Altium Designer software. This should fill out all the required options in here, so you won't have to worry about that. And then you share this cart with the EE department for purchasing. But I kind of went through that pretty quickly, but I hope that's helpful. Just to go over a summary, we created a nice little schematic together. We created a little power converter. We created a PCB document with our input connectors and output connectors. Had a nice little 3D model to, had a nice little 3D model to kind of show off the different aspects of like laying out a PCB. And then we defined a stack up and then made sure, we defined a PCB stack up and then made sure that our rules were consistent with what we needed to do. Alright, now I will say that this design is definitely pretty simplistic, and there's a lot of things that we didn't use and didn't really showcase in the tutorial, that they are pretty advanced. I'm going to link to a lot more videos that can maybe provide specific guidance in certain aspects of different projects that you might be interested in doing. But again, if you have any questions related to Altium Designer and PCB design, please reach out. I'm more than happy to answer your questions. I'm also going to announce my office hours, which will be a weekly time, and I hope to answer your questions there. Alright. Thank you for watching, and I hope to see you soon.